now you have a better understanding of where linear regression has to be used on what type of data set. And what do you mean by simple linear regression, multiple linear regression, and how the regression lines are being constructed. Okay, with that, we'll continue this session. So a small recap, this is what we have seen in our last session. So it is like when we say that there exists a linearity between any two attributes. These attributes are otherwise called as your independent variable and your dependent variable, right? The dependent variable is otherwise called as a response variable or an output variable. The independent variable is otherwise called as your input variable or a predictor variable. Okay. So when you try to plot a graph between the input variable on the x-axis and the output variable on the y-axis, if there exists a linearity means what? If there happens to be an optimized straight line. Okay, why am I telling optimized? Because in real time, when we go for machine learning data sets, you cannot always expect a straight line. There could be points of this kind which is shown over here. Okay, and we have seen the once the optimized straight line is being drawn, okay, the difference between the calculated value and the actual value is what we call as the error term. Okay, so that error is what we need to minimize. So coming back here, how to construct this straight line, because we say the points are distributed on space, right? So between the coordinates the points are distributed, and hence we are in need to draw a straight line connecting most of the points, thereby reducing your error, right? So that is our ultimate aim. So how will you do that? That becomes the question here. For an example, I have drawn two different straight lines that you can draw from the initial point to the end point, right? So black represents one line and the other straight line is also drawn. Okay, so how to choose which line is the best? It depends on how much error are we getting. Okay, how to calculate the error? Just for every point we need to identify how much is the error. Okay, so for this point, how much is the error to this line or to this line? Everything we have to finally add up, take an average. That's what we call it as the error. Okay, so this mean error term is what we calculate. So whichever line is reducing that error will be considered most useful. Okay, so this is impractical, right? But now we want the machine to do this for us. How to do? That is the next question we need to answer. Okay, so how to do? So that line construction, for constructing a line, we are in need of two basic parameters. One is the slope, another one is the intercept. Okay, so these are the two values that we are going to calculate here. Let us see how this could be calculated. There are two basic methods. Actually, least squared method is the most popular method or a statistical method used for computing the slope and the intercept. Okay, be it in a simple regression or multiple linear regression. Using the partial derivative method, least squared methods compute the values of the slope and the intercept, and thereby giving you an optimized line. There is also one more concept in machine learning, which is gradient descent method, which is of more use. Okay, so to start with the randomized values of M and C and to arrive at a more optimized value. So we'll have a session in detail to understand what gradient descent methodology means to us, right? So as of now, we'll move with least squared method. That is the solution that is available in scikit-learn library also. Okay, so just to brief about how it comes. Okay, just follow me. It's a simple mathematical concept that we need to understand. Assume that the line we are going to construct is y is equal to mx plus c. Okay, so this is what we are going to construct. And what is the error term? How to identify the error? Assume that y is equal to mx plus c, wherein yi is your calculated value, right? Already in our data set we already have a actual value, right? For example, you take the placement data for the year 2000. What is the value of y? We already have. For the year 2001, what is the value of y? We already have. So this goes on from 2000 till which year? 2020. Okay, so with 2000 to 2020 we already have the data. That is what we call it as the y. Okay, so this capital Y represents your calculated value. Okay, so this is actually your calculated value. So When there exists a difference between the actual value and the calculated value, that is what we call it as error, right? So why are we squaring it? Okay, because we want to remove the absolute nature of it. Okay, for example, if there exists a negativity while going for subtraction, if the predicted value is more when compared to your actual value, you'll be left out with the negative value, right? When your predicted value is less compared to your actual value, you'll be left out with the positive value. We never bother about the sign, but we bother about only the magnitude of it. Okay, how much is the difference? And hence, in order to bring in that magnitude, we are squaring it. By squaring it, the sign will get lost, right? So this we have to repeat for all the n points, where n represents the number of what? Yes, the number of experiences we have. How many ever number of rows you have, that is what. Okay. So summing up of all the errors will give you the total error that happens because of constructing a straight line to accommodate that particular data set. Right. Now, in the next line, I have substituted this capital YI with its formula, because the small yi, if you take, it is all just numbers. Keep in mind, it's all constants, right? Which we already have as part of our data set. But if you look at capital Y, this is being computed using this formula. Okay, and hence these are all variables. You have to substitute. Okay, so this is a constant and this is a variable. Why am I stressing this? When you go for taking partial derivative, this terms will become 0 because it's a constant, whereas this is a variable. Okay, I just have substituted. So now, what are the variables we have over here? So our intention is to find small m and small c, that is slope and then the intercept. So we have to partially differentiate this equation with respect to m and with respect to c. So what is our intention? We want to make the error to be 0. That's why we have equated the line to be 0, right? So if you partially derive these two equations, ultimately we end up with this thing. So this is what is the equation that we normally use to calculate the values of m and c. Okay, what is that c? It is nothing but the point where the line crosses your y-axis. Okay, when x is equal to the base value. Here the base value is 2000, and hence we say this is your intercept. Okay, so otherwise in general it is origin. When it crosses your origin, when x is equal to 0, we say that is your intercept. It casually, if you look at, that is the common bias that prevails in the system. Okay, so if the placement strategy from the years 2000 to 2020 starts with 50, we say 50 is the intercept. Okay, because all the values will be aligned above 50. We don't need to bother about the values beyond that. Okay, that's what we say intercept. And what is slope? Yes. So when you increase 1 unit, here what is the unit in year? It is 1, right? 2000 to 2001. When you increase from 2000 to 2001, how much is the difference in the y direction? Dy by dx. Okay. So the difference in x, how much is the impact in difference in y will be calculated using this, will be defined using this m. Okay. So in order to tilt this line, in order to reduce your error, we need to change this m. Okay, because intercept also you can change, because when you tilt this line, the intercept may go down or move up, but too much of variation will not be there. But if you logically think, this m value alone will decide, okay, whether it will be tilted above or down. Okay, now with this, these are the values that will be resulted after partially derivating that equation, loss equation to us. Okay. Now suppose if you have multiple linear regression, then how is it being arranged? Okay, it's very common like your simple linear regression. The only difference is in simple linear regression, will be taking only one input variable, or otherwise called as your predictor variable, whereas in multiple linear regression you can use that is, you can have any number of input variables. Okay, so and the equation will be like m1 x1 m2 x2 and so on, as many number of attributes you have plus c. Okay, but the error equation remains same. Okay, how many ever be the number of input variables you have, our output variable will always be same. If that is the case, what to do? You just have to reduce the error. Okay. So now again replacing, now will be having three terms. Actually here by mistake I have given only one. Actually this entire equation has to be substituted here. Okay. Now, if you do that, you will have three different parameters, m1, m2, and then c. Okay. So, you have to partially derive with respect to m1, m2, and c. If you do like so, you can retrieve the values of m1, m2, and c. Okay. So, that's what your multiple linear regression does. Okay. So, having understood this simple linear regression and multiple linear regression, you should now be able to define, okay, what an error term is, how the values of slope and intercept is being calculated. When it comes to multiple, that is having multiple attributes, how is it being done? Okay, all these things you should be clear before moving on to the next session, where we'll be discussing about the performance metrics that is available for linear regression. Okay.